Hello everyone and a very warm welcome. You're watching Kognito Key, and today we're going to unlock a really cool secret in the world of magnets.
Yes, welcome to Kognito Key. Our whole mission here is to take these big, complex ideas and just make them simple. And today, we are demystifying a concept that's at the very heart of magnetism.
Have you ever thought about it? Why a magnet will just leap onto a piece of iron, but it completely ignores something like wood or plastic? It's almost like some materials roll out the red carpet for magnetism, while others just slam the door shut. Well, guess what? There's a scientific reason for that, and that's exactly what we're going to get into today.
To really get our heads around this, let's start with a really simple but powerful analogy. I want you to think of magnetic fields like traffic, okay? And just like traffic, they're always looking for the easiest, fastest way to get where they're going.
So let's imagine you have a magnetic field just out in the open, in a vacuum or even just in the air. The magnetic lines of force are actually pretty well behaved. They travel from one pole to the other in these nice, straight, predictable lines. There's really nothing getting in their way to change their path.
But what happens if we put something in the middle of this field? Let's say we take a ring made of soft iron and we place it right there in the path of those magnetic lines. And this is where it gets really cool. Just look at that. The magnetic lines, they completely ditch their straight paths. They all bend and crowd together because they'd much rather travel through the iron ring than through the air around it. The ring is basically a superhighway for them. It's just a much, much easier path to take.
Okay, so this superhighway effect, this has a proper scientific name. It's called permeability. It's the official term for how easily a material allows these magnetic forces to pass right through it. So let's get a formal definition.
And there it is. Magnetic permeability is simply the property of a material that allows those magnetic lines of force to pass through it. So a high permeability, like our iron ring has, means that material is super welcoming to magnetic fields. And of course, like with any scientific property, we need a way to measure it. The standard unit that's used for magnetic permeability is the Henry per meter. Here's another great way to think about it. Permeability is really a measure of how much a material can support and even strengthen a magnetic field inside of itself. So the iron ring doesn't just let the field pass through, it actually helps concentrate it. All right, for those of you who like to see how things are calculated, this whole relationship can be put into a very simple formula. And don't worry, it's really quite straightforward.
The formula is just this: mu equals B divided by H.
So in this equation, that Greek letter mu is our magnetic permeability. And we find it by taking B, which is the magnetic flux density. That's basically how packed together the magnetic lines are. And dividing it by H, the magnetic field intensity, which is the strength of the outside field. See, it's a simple ratio. Okay, so knowing the exact number for iron's permeability is useful, for sure. But what's often even more helpful is comparing it to something else. Like, how much better is iron at conducting a magnetic field than, say, the air around it? And this is where the idea of relative permeability comes into play. And the difference is huge. On one side, you have iron with its super high permeability, creating that lovely superhighway for magnetic forces. And on the other side, you have air or a vacuum, which has a very low permeability. It's more like a bumpy, difficult country road that kind of resists the magnetic field. So relative permeability is exactly what it sounds like. It's a comparison. It's a ratio that tells you how many times more permeable a material is compared to a complete vacuum. And that permeability of a vacuum gets its own special symbol, mu naught. And the formula is just as simple as it looks. You take the material's permeability, mu, and you divide it by the permeability of a vacuum, mu naught. And that gives you its relative permeability, or mu r. And this is what makes it so useful. Since air and other things that aren't magnetic have a permeability that's almost exactly the same as a vacuum, their relative permeability is just 1. It's our baseline. So if someone tells you a material has a relative permeability of, say, 5,000, you instantly know it's 5,000 times better at conducting magnetic fields than air is. Simple. So let's just quickly wrap up what we've learned. Permeability is basically a material's permission slip for magnetic fields. Materials like iron create that easy path, while air creates a really difficult one. And relative permeability gives us a nice simple number to compare them. And understanding this is absolutely crucial for designing everything from electric motors to magnetic shielding for sensitive electronics. And there you have it, the secret language of magnets unlocked. I really hope this helped you understand these invisible superhighways all around us. If you found this explainer helpful, please do give it a like, share it with your friends, and of course, subscribe to Kognito Key for more. Thank you so much for watching.